Hi, Assalamualaikum. My name is Nur Amnani Sofia, and today my group would like to present about the Lenstar. So the purpose we present these ophthalmic instruments is to gain knowledge about the Lenstar, such as its components, optical principles, functions, and so on. First of all, Lenstar is a non-invasive and non-contact LSCR, which is optical low coherence reflectometry biometer that used in the calculation of intraocular lens power through different formulas. Basically, the system is divided into two parts, that one concerned with examination, LS900, and the other with control like notebook and PC. So the examination part communicates via a USB connection with the external PC. The LS900 is also operated using the iSuite software that installed on the PC. Last but not least, integral automatic error recognition for measurements guarantees reliable examination results.
Thank you to Sophia for the lovely introduction. Assalamualaikum warahmatullahi wabarakatuh. My name is Nofatini and I will be continuing the presentation for the parts of the Lenstar. The images in the slide show the Lenstar instrument that we have in our clinic. The Lenstar components have two parts, which are the Lenstar itself for the examination and the other one is the PC. The examination part is connected to the PC via a USB connection. The Lenstar 900 is operated using the iSuite software installed on the PC. Let's start with the first part of the instrument's component. The first one is the front ring, which is to fit in a T-cone, where T-cone is used for topography. And the second one is housing, where it houses the mechanism for the Lenstar instrument. And the third one and the fourth one is the service cover and the cable cover, which both hold the same function, which is to cover the whole Lenstar mechanism. And the fifth one is the control lever. The joystick is used to position the device aligned to the patient's eye. It is used to move the instrument in directions such as left, right, upward, and downward to match the patient's fixation. And the sixth one is the type plate, where there is a description of the type of plate for the Lenstar. And the seventh one is the site identification sticker for Lenstar unit identification. Continuing with the eighth component, which is the headrest. The ninth one is the headband, and the 10th one is the mark for the optimum eye height, which is to make sure the patient Cantor's mark is aligned with the mark given. And the 11th one is chin rest, the 12th one is chin rest height adjustment, and the 13th one is hand grips for patient. These parts are created to make sure patient has a steady head position by putting their head on the headrest and making sure their forehead is touching the headrest, and their chin is touching the chin rest, and patients should also hold on to the hand grips to make sure they are in a stable position. Moving on to the 21st component, which is the device state indicator. This device allows device monitoring without using the PC software. For example, dark means off, orange means standby, green means on, blue means the light source is on, and red means error. The 22nd component is the trigger, which is used to start the measurements on the eye. Next, component 23rd until 27th, which are the 23rd one is the USB device connection, the 24th one is the DC device connection, the 25th one is the USB 2.0 cable, the 26th one is the DC cable, and the 27th one is the cable tension compensator. All these components in the Lenstar connect the Lenstar to the PC monitor to obtain the result through the software. So for the last part of the components, number 28 is the tabletop, number 29 is the left hand drawer where there is the switch box, and number 30 is the right hand drawer, which is usually empty, and number 31 is the elevator column where there is a mechanical with spring. So this component will allow the instrument table to be adjusted accordingly to make sure the height of the device is set at a comfortable height for the patient. And the last one is the 30-second component, which is the stand base with casters to move the instrument table around easily. That's all from me. I will pass my presentation to the next presenter. Thank you.
Next, we move to the optical principle of the Lenstar. The Lenstar use OLCR, which is the optical low coherence reflectometry. OLCR use 820 nm superluminance diode in a standard Michelson interferometer setup. In this biometer, the optical path length measurements are aligned on the visual axis of the patient's eye, and a specialized rotating glass system embedded in the machine changes the optical path length. Hence, it can measure not only the axial length and cornea curvature, but also the central cornea thickness, lens thickness, retina thickness, and also the pupil diameter. The diagram below shows the measurement that has been taken by the Lenstar, which are axial length K1 and K2 value and the astigmatism. So how actually it works? Firstly, light source and emission. As mentioned before, the Lenstar uses superluminous diode that emits a near-infrared light pulse with a broad bandwidth. This broad bandwidth ensures that the light has multiple wavelengths traveling within a very short coherent length. Second one, reflection and interference. The light pulse travels through the eye, reflecting off different internal structure like the cornea, lens, and the retina. Each reflected wave carries information about the distance it travelled and the reflective interface it encountered. Next, backscattered light analysis. The backscattered light from the various structure returns to the instrument. Due to the short coherent length, only reflected light within a specific distance range around the source will interfere constructively, creating peak in the received signal. Analyzing this peak with sophisticated algorithm allow the Lenstar to determine the depth and location of the reflecting interface within the eye. Lastly, data processing and measurement. The OLCR data is further processed using the ISO software in the Lenstar. The software utilizes predefined refractive indices for different ocular structure and calculate the actual geometrical distance, such as axial length and lens thickness, based on the optical path length measured by OLCR. Okay, so next we move to the connection between the optical principle and the functionality of the Lenstar. As we know, Lenstar can acquire more parameters such as cornea thickness and the intraocular lens thickness, as it can capture all measurements simultaneously without the need for realignment. OLCR used with the Lenstar has a stronger penetrating power and a higher signal-to-noise ratio. For the anterior-chamber depth measurement, Lenstar used OLCR technology to scan 16 times in one measurement to detect the cornea thickness from epithelium to endothelium and the distance from the endothelium to the anterior surface of the crystalline lens. For the K reading, Lenstar take reading in two circles, which is 16 points in each circle. The diameter of the inner circle is 1.65 mm and the outer circle is 2.3 mm.
Bismillahirrahmanirrahim. My name is Lena. So I will explain about the function of the Lenstar LS900. So now in this presentation, I will divide it into three parts, which consists of the comprehensive overview, real-world applications, and users' perspectives. Lenstar LS900 is famously known for its accuracy of laser optic measurements that cover a broad area due to its ability in capture 9 biometric parameters in one shot. Based on my studies, the real-world application for Lenstar LS900 can be highlighted into three practical significance. So, firstly, Lenstar LS900 is highly accurate measurement for cataract planning due to its application of Fourier domain A-scan technology that able to speed the process makes it able to penetrate almost all dense cataract. And secondly, Lenstar LS900 is a valuable tool for cataract surgery and IOL placement due to the 9 biometric per shot. And lastly, Lenstar LS900 saves time and increase patient comfort because they use the technology called APS, Automated Positioning System, that makes the examiner to easily make sure that the patient is in a comfortable position while doing the procedure. for my last part, I will explain about the user's perspective and how Lenstar LS benefits either the patients or examiners. Based on the data collected, I got two users' perspective about the Lenstar LS900. So for the first one, Lenstar LS900 is the IOL power calculation due to the advanced Olsen formula and methods. IOL power is a crucial data to obtain after refractive surgery for further observation towards the progression of healing. Last one, Lenstar LS900 obtained complete biometric measurements that cover CCT, ACD, LT, axial length, and retinal thickness due to the 9 biometric parameters in one shot. Now, I pass this to Sister Rahima for the calculation for this presentation.
Lastly, for the conclusion, the Lenstar LS900 has proven to be a valuable tool in modern ophthalmic practice, offering a non-invasive and efficient in obtaining accurate measurement critical for optimal surgical outcomes. Its ability to capture a broad range of ocular parameters such as axial length, corneal curvature, anterior chamber depth, and lens thickness. The OCT technology allows for the high-resolution imaging for ocular structures, contributing to the detailed assessment of the eye's anatomy. This results in enhanced the accuracy of calculation, particularly in the cases with atypical corneal shape. This Lenstar LS900 have a user-friendly interface and automation features to ease the use and effort and efficiency in a clinical setting, as it minimizes the margin for the error and facilitate the smoother workflow. Lenstar LS900 stands a reliable and sophisticated biometer, play a crucial role in the pre-operative assessment for cataract and refractive surgeries. Its comprehensive measurement and advanced feature contribute to the precision and predictability of surgical outcomes, ultimately benefiting both the surgeon and the patient in achieving optimal visual results. That's all from us. Thank you.